All right, welcome everyone to today's QGI Seminar. Today we're very happy to have Alex May from UBC, who's going to tell us about entanglement and light cones in AdS CFT. So Alex, please take it away.
Great. Well, thank you first of all for the invitation. It's a pleasure to be here, if only virtually. So yes, as was said, I'm speaking about entanglement and light cones in AdS CFT. And this is based on a few papers in a general line of work, but most specifically, I'm going to talk about this paper, which was done in collaboration with David Wycombe, who's another graduate student at UBC with me. Okay, so I'll start out by reminding you of a few things you already know. So we know, of course, that quantum information at this point plays a very significant role in our understanding of AdS CFT. And one of the backbones of this connection is, of course, the Ryu-Takayanagi formula. So in maybe its simplest form, what this says is if you'd like to calculate the von Neumann entropy of some subregion of your conformal field theory, then the way that you should do that is you should look at all of the surfaces, let's call them gamma, which are homologous to V. Homologous means this here, so there should exist some codimension 1 surface S whose boundary is V union gamma. You should look at all those, you should minimize over them, take the one of minimal area and divide its area by 4G Newton, and up to some order 1 corrections, that will be your entropy. Okay, so on the one hand, this relates entropy or entanglement in the CFT to geometry in your AdS space, and in particular geometry as captured by minimal surfaces. Okay. Another thing to mention about this is that the surface S that's picked out by the actual minimal surface, so let's call it S star or something, this S is what's called the entanglement wedge, and it has an important role in that it's the portion of the bulk recorded into the density matrix of the subregion B. Okay. Good. Okay. Now, these things have been very interesting and taught us a lot, but one recent and exciting thing that where this has come up is in our understanding of black holes. And maybe two things that we've learned there is one, using this formula, how to derive the page curve from bulk semi-classical calculations. Okay. And then two, based on this understanding of entanglement wedge reconstruction, we've understood when the radiation that's escaped from a black hole can be used to reconstruct the interior of the black hole. So now there's this now famous picture of the one-sided evaporating black hole, and we've learned that if you collect enough of the radiation that's come out, you can reconstruct some portion of the interior, and that portion is called the island. Okay, good. So this is sort of old news, but what I want to do today is to take a bit of a different perspective on quantum information and its connection to AdS CFT. And in particular, that's going to be a perspective that emphasizes relativistic aspects of quantum information and really how quantum information can be processed in the context of spacetime. And we'll see that by taking this perspective, we'll find a connection between causal features of the bulk geometry and entanglement in AdS CFT as distinguished from minimal surfaces relating to entanglement. So to make that more precise, what I mean by that, let me tell you about a theorem. So the theorem is called the connected wedge theorem. And the way it works is the following. So you should, first of all, pick 4 points on the boundary of your AdS space. So I've drawn an example here where my points are C1, C2, R1, in R2. And then what you should do is you should check if those 4 points scatter in the bulk. By scatter in the bulk, I mean there's somewhere in the bulk, let's call it P, which is in the future of C1 and future of C2 and past of R1 and past of R2. In other words, this spacetime region I'm defining here, which we'll call the scattering region, we're looking for cases where that scattering region is not empty. Okay. And then what the theorem concludes is if that region is not empty, then the mutual information between two associated boundary regions is order 1 over G Newton. Okay. And specifically, the boundary regions of interest are these things I've drawn in green here called V1 and V2. They're defined by taking, say V1 is defined by taking the future of C1 in the boundary and intersecting with the past of R1, which comes down like this, and the past of R2, which comes down like this. Okay. So that's what the theorem says. There's another way to understand this, but just noting that, okay, this mutual information being large is equivalent to the Ryu-Takayanagi surfaces for V1 and union V2 sitting this way. So the entanglement wedge of V1 union V2 should be this connected region in here, as opposed to being this disconnected surface like this. Okay. So you can also say, okay, this scattering region being not empty means that this entanglement wedge is connected. Okay. Are there any questions about this theorem? May have seen me speak about this before. Okay.
Actually, if I can ask a quick question. Yeah. So is this in vacuum, or is this like in whatever geometry you have in the interior?
Yeah. So the proof just assumes that the null energy condition is true.
Okay, cool.
In the vacuum, it goes in both directions. But in general, it goes in one direction, but it is a true statement. Yeah.
Cool, thanks.
Okay. So this is the connected wedge theorem. This is relating, on this side, features of bulk light cones. So we're looking at some overlap of 4 light cones. And then on the boundary side, it's relating that to correlation in the conformal field theory. Okay. Yeah, and I'll say that this part of the theorem doesn't use the Ryu-Takayanagi formula. It's logically independent of the RT formula. It's only when you want to then relate it to this entanglement wedge being connected that then you bring in the RT formula. But you can show this without ever discussing RT. Okay. Okay, good. So that's what I mean by causal perspective on entanglement. Yeah, Dominic?
Can you go back for a second?
Yeah.
I have a question about the last sentence you said.
Yeah.
You can prove this theorem without using the RT formula. So yeah. How do you compute the mutual information?
Yeah, so I'm not going to argue for this theorem, but I will at the end of this talk give an argument for a very closely related theorem. So you'll see the quantum information argument to get here. But yeah, you use a separate argument, not RT, to show that this mutual information has to be large.
Okay, so you use a CFT argument to make a statement about the mutual information?
You basically, okay, basically you argue that you can imagine like some quantum systems coming in along these lines. So let's say A and B, and then something happens here. I don't know, some unitary, and then some other systems come out, C and D, and using quantum information techniques, you can show that for the boundary to reproduce this unitary, like for the same unitary to happen in the boundary, you need a bunch of entanglement between the two green regions. Yeah, that's very quick and heuristic, but you'll see a detailed version of this later.
Okay. Well, thanks.
And yeah, the gory details are here, if you're. You know. But yes, I'll sort of postpone this question, and we'll come to that.
Cool.
Good. Okay. So this is, you know, one concrete realization of what I mean by a causal perspective on entanglement, and the main goal for today is going to be to take that perspective on entanglement and see what it tells us about black holes and islands, right? So we know that the RT formula, this perspective of relating entanglement to minimal surfaces, tells us a lot there. Well, we're going to try and take this other perspective and see what it says. Okay, so that's the goal. And then the roadmap to get there is the following. So I'm first of all going to talk about what's called AdS BCFT. I think some people here are more expert than I am on this, but it's okay also if you don't know anything about it. You won't need to know very much. And I'll tell you what you need to know. What AdS BCFT is, I should say, is some kind of holographic duality for a conformal field theory that lives on a manifold with a boundary. And that's going to be the setting in which we'll construct some solutions that will serve as our black hole solutions. Okay. And then second, I'm going to state a theorem similar to the one that was on the last slide, but that's adapted to this context of AdS BCFT. Okay. And then next, I'm going to put those things together. So I'm going to apply this connected wedge theorem to these black hole solutions and see what we learn there. Okay. And then finally, I'll come back to more properly justify this connected wedge theorem, and I'll give you a quantum information argument that I'm calling a quantum tasks argument for this AdS BCFT version of the connected wedge theorem. Okay. So if there's any further questions, you can take them. Otherwise, I'll jump in. Okay. Okay. So let me just start by summarizing a few things about AdS BCFT. Okay. So it's some kind of duality. I'm going to start by giving you the bulk picture. So the bulk picture is we have our AdS space, right? So we have some action. We have the usual Einstein-Hilbert terms. We can have some matter Lagrangian as well. And there's some asymptotically AdS region. So that's the AdS boundary. And then additionally, and different than usual, there's some dynamical object in the bulk, which we'll call the end-of-the-world-Brane, on which your spacetime ends. Okay. That object has its own action, which is what I've written down here. The action is written in terms of the induced metric, the extrinsic curvature, and then some matter Lagrangian for fields that are localized to the brane. Okay. Good. Yeah, and then with that action, you can get some equations of motion. You'll get the usual Einstein's equations governing the dynamics of the bulk of AdS. And then additionally, you'll get some equation governing the dynamics of the brane. And one comment here is just that the stress tensor appearing here is coming from the matter fields localized to the brane. So this is like some delta L B matter by delta G. Okay. So that's the basic elements of the bulk picture. Oh, I should say that the brane here will extend out to the AdS boundary. Where the brane meets the boundary, which I've drawn in orange here, I will call the edge. Okay, just as a piece of terminology. Okay. Okay, good.
And is this TMU on the brane in the boundary description some boundary degrees of freedom, or where does it live in the CFT?
Yeah, I will hopefully answer that in this slide. If that's okay. If I don't, ask me again. Okay, so in the CFT, let me give you the CFT picture. Well, okay, so here's a time slice of the picture I drew on the last page. So we have our AdS space, we have our AdS boundary, we have the end-of-the-world-Brane, and then where the brane is meeting the boundary, we have this thing called the edge. Okay, and then the dual description of this is going to be the following thing. So there'll be a CFT that lives on the AdS boundary, and then the CFT will have some boundary condition on it that's fixed at the edge. Okay. The boundary condition, we can pick many different boundary conditions. And in my context, I won't need to give you a microscopic description of the CFT or of the boundary condition. I'll just need to keep track of a few parameters here. And so there's going to be some parameter describing the CFT boundary condition, which is just this number called the edge central charge. And roughly it measures like the number of degrees of freedom that are kind of localized to the edge. Okay. Good. Okay, so that's the general picture. And then for the solutions I'm going to consider here, we'll take a simple case where the matter Lagrangian on the brane will just be proportional to sorry, I've lost writing ability. Sorry, one moment. My tablet's frozen. Sorry. Okay, I'm back in business. Okay, so I'm going to pick a simple form for the matter Lagrangian on the brane, which is just going to be proportional to some constant t, called the tension, and that leads to a stress tensor that looks like this. So it's just proportional to the induced metric. Okay, right, and then there's some parameters describing the bulk here and some parameters describing the boundary. So let me tell you how they're related. In the bulk, we have this AdS length, and we have a tension T describing the brane. In the boundary, we have the CFT central charge and the edge central charge, and these quantities are related this way. So the CFT central charge and the bulk AdS length are related by the usual formula, the Brown-Hinault formula, and then the brane tension is related to the edge central charge in this way. Okay, good. Okay, so that's pretty much everything I need to tell you about AdS BCFT. I'll just tell you one more thing, which is that Ryu-Takayanagi, at least understood carefully, is still true. So what you have to do here is just understand the homology constraint carefully. So in particular, we're going to minimize over surfaces gamma that are homologous to V, but homologous here means this. So it means that there's some codimension 1 surface S whose boundary is V union gamma union any portion of the brane. Okay. And so that, in practice just means the following things. So if I have some boundary region here, V, there's two classes of surfaces homologous to V, one class that sits like this, doesn't touch the brane, and another class that sits like this. Okay, and so this would be what I'm calling little b. And yeah, both of these are homologous to v, so we have to pick the minimal one between these two. Okay, good. So that's AdS BCFT, and then the solutions I'm actually going to use are the following things. So I'm going to work in d equals 2, or AdS 2 plus 1, and I'm going to take this simple choice for the matter Lagrangian on the brane, where I just have a constant tension, and I'm going to take pure AdS in the bulk. So the bulk matter Lagrangian is just 0. Okay. So then, you can write down these equations I had before. You can find some solutions. Here's the solution we're going to work with. We have pure AdS in the bulk, okay, which I've written in a funny way. I've written it in these with this row coordinate. So here we have the metric of a lower dimensional AdS. So this is just AdS 1 plus 1. And then all these factors of AdS 1 plus 1 are warped together with this row coordinate to form a full AdS 2 plus 1 spacetime. This is a convenient set of coordinates because we have these solutions where the brane will just sit at a constant row value here. Okay, controlled by the tension. Okay, so for t equals 0, your solution looks like this. Your brane just sits down the middle of AdS, and you have half an AdS spacetime left. For negative tension, your brane comes in like this. You have less AdS spacetime. And for positive tension, your brane sort of bends out, and you have extra AdS space. Okay. Okay, so those are our solutions. Good. Okay, so now I'm going to state a version of this connected wedge theorem that will apply to AdS BCFT and sort of these bulk AdS spacetimes that have these end-of-the-world-branes in them. Okay. Okay, so here's the theorem. I'll just state it again. Now we're going to pick 3 points, and we're going to pick a point C1, which will be in the AdS boundary. And then we're going to pick R1 and R2, which will both be in the edge. Okay. And then what we do is we check, do these 3 points scatter off the brane? Okay, so by that, I mean that there's somewhere here, which I'm calling J1 goes to 1, 2, which is in the future of C1 and the past of R1 and R2, and is also on the brane. Okay. And then what the theorem says is that if that scattering region, or that brane anchored scattering region, isn't empty, then the entanglement wedge of this boundary region here, V, okay, will take on the attached to the brane configuration. Okay. So it will attach this way. And okay, more precisely, V is defined just like before. So it's the future of C1 and then the past of R1 and past of R2 taken in the boundary geometry. Okay. So like I said in the outline, I'm going to give a detailed argument for this in the last section. But I'll state now that, so there's a quantum information argument for this, and then there's a relativistic proof of this. The proof just assumes these things. So it assumes the null energy condition on the bulk stress tensor, and then also the null energy condition on the brane's intrinsic stress tensor. So this is that intrinsic stress tensor I mentioned before. And then LA and LB are null vectors that are tangent to the brane. Okay. So with these two conditions, you can just prove this theorem. Okay. Good. So that's what I'm going to use. Well, actually, it's not quite what I'm going to use. I'm going to use its time reversal. So, GR is a time reversal invariant theory. So I can just switch all my forward to backward light cones and backward to forward light cones, and I'll still have a true statement. So now the theorem looks like this. I have R1 and R2 that are at some early time, and then C1 at some late time. And then we check, if these meet up on the brane and then get out to C1, then that means that this region up here will attach to the brane. Okay. Any questions about the statement of this theorem? Similar to the other one, but. Yep.
So is this equivalent? So a different perspective of a very related geometry is not one in which the spacetime ends on the brane, but rather in which you glue an identical copy on the other side, right?
Yeah.
And you can just pass through the brane with no problem.
Yeah.
If you apply your first theorem, or let's say that the previous version, to that geometry, is that identical to what you're doing here?
It's related. So in some cases, this statement follows from doing what you're describing. But there's a bit of this is a little bit more general actually, in that the conditions for the last theorem were that the null energy condition was true. So you needed this. And then there's a lot of cases where when you do this doubling procedure that you talked about, the stress tensor in that doubled geometry won't satisfy the null energy condition. But this theorem is actually still true. So if I say I took a brane with a tension that's negative, okay, and so it has a stress tensor like this. Then when I double this, I will have some bulk stress tensor that will have like a delta function, and then minus t, and this will violate the null energy condition. And so the earlier theorem wouldn't conclude anything about this geometry. But the point is actually that this imposing the null energy condition on that entire double geometry is too strong. You only need this, and this kind of a stress tensor with a negative tension would still satisfy this condition here. So the doubled picture would miss this case of negative tension, but the direct argument sees that the theorem is still true there.
Okay. But in all of these cases, the induced metric on the brane is AdS2.
Well, it doesn't need to be. So in the particular solutions that I introduced before and that we're going to use, it was exactly just a copy of AdS1 plus 1. But the theorem here is true more generally. You can have whatever stress tensor whatever metric on the brane that you want, as long as the you're satisfying that condition relating the induced metric to the intrinsic stress tensor, and this is satisfying this version of the null energy condition.
Okay. Thanks.
Yeah. So yeah, I mean, it's a very similar theorem, and for simple cases, this is just cutting the other geometry in half, and you can sort of guess that this is true by the sort of procedure you're talking about. But if you're a bit more careful, you get a bit more of a general statement. Yeah. Okay. Good. Okay, so I've described AdS CFT. I've described some particular solutions that I'm going to get back to, and this connected wedge theorem. I'm going to try and tell you now what this connected wedge theorem tells us about islands. Okay, but before I can do that, I want to argue that there is a black hole in these solutions that I've been describing. And so here's these constant tension pure AdS solutions. So the bulk is pure AdS. This is some t equals constant. And I could write down that metric that I had before. And then what I claim is that looked at in the right coordinates, the geometry of this brane is the geometry of a black hole. And okay, one way to see that is to take a Poincare patch. So so my solution here is only a portion of global AdS because it's cut off by the brane, but I've just drawn schematically where the rest of global AdS would be. And I will take a Poincare patch in these of this solution. Okay, so in the global spacetime, that would look like this usual kind of a wedge picture. But in my end-of-the-world-Brane solutions, I just get a portion of that Poincare wedge. And that portion is bounded by the end-of-the-world-Brane here. And then these two sort of triangles or wings of the CFT, right? So I have this sort of chunk of the spacetime picked out. Right, okay, something you can notice is that the amount of the brane, the time extent of the brane that will be included in the patch is time pi in appropriate units. And then the light travel time across the global AdS, across the brane, I should say, is also pi. And so that means that this edge here, the portion of the edge on this side that's inside the patch and the portion of the edge on this side that's inside the patch are separated, are causally separated. So there's some horizon here separating these two ends of the brane. Okay. And so those horizons are going to be the horizons in my black hole, and the two edges are going to be the asymptotic regions for this black hole. Okay. Yeah, so I'm not really saying anything too surprising here. I already said that the geometry of this brane was AdS 1 + 1, and people who think about AdS 1 + 1 will be familiar with the statement that viewed in the right way, it's like a black hole. Okay, so that's my black hole. It's in the brane, and it's apparent in this patch. Okay. The next thing I'm going to do is I'm going to focus on a special case here. I'm going to focus on the case where the tension is large. Okay. That is nice for two reasons. The main reason it's nice is that in the limit of large tension, the black hole, i.e. the brane, is described by the degrees of freedom that live at the edge. Okay. And one way to see that is to think about like a small interval near the edge, okay? And think about its entanglement wedge. When the tension is small, these surfaces will be minimal. Okay, they'll be less in area than this. But if I push the brane out far enough, these will get longer and longer, and eventually this will become your minimal surface. Okay. And so in that case, the entire brane, i.e. the entire black hole, is described by just the edge degrees of freedom. Okay. Another reason large tension is nice is because this sort of fits with early ideas by Randall and Sundram, who pointed out that large tension branes in AdS have a lower dimensional effective gravity localized to the brane. Okay, so we can, in this case, we can also think about there's a lower dimensional description of gravity that's just intrinsic to the brane. Okay, good. So that's my black hole. In the bulk, it's the brane. In the boundary, it's the edge. And then the final piece is that we're going to say that the rest of the CFT is the radiation system. Okay, so we have this edge, okay, which is the black hole. So if I wanted to draw the bulk, if I wanted to draw the black hole, it'd be some brane here. It's beyond the brane here, and then information can escape, or potentially can escape from the edge. edge into the rest of the CFT. Okay. So the CFT is the radiation. Okay, so this is, basically the same as the doubly holographic models that are very popular. It's just in a bit of a different language of this boundary conformal field theories. Okay. Okay, I'm going to skip this, and then I'll just say that what we want to do, and what people have done elsewhere, is think about how much of the radiation or which portions of the radiation system do we need to reconstruct the interior of the black hole. Okay. Okay, good. So there's two ways to do that. So there's two ways we can look at the radiation system and understand whether or not it reconstructs the interior of the black hole. The first is the minimal surface way, the RT surface, the RT formula way. Okay, so in the particular model that I've set up, this was done already by these authors at UBC. So Moshe Razali, Jamie Sully, Mark Van Remsunk, Chris Waddell, and David Wakeham. Okay, so what they did is look at subregions of the CFT. So maybe I'll describe these pictures a bit better. So if we go back, what I'm drawing here is the square I'm drawing is this chunk of the brane here. And then the two triangles I'm drawing are these blue regions folded flat. Okay. So that's this picture here. Okay, so these authors, they studied this problem. They looked at subregions of the CFT. So let's say these orange regions here, and then looked for the minimal surfaces enclosing that orange region, right? And then just checked by a minimal surface calculation if this was minimal or if this was minimal. Okay, and in that way they could see that at later times when you've collected more radiation, then you reconstruct a portion of the interior of the black hole. Okay. Is that clear? Sometimes people I'm drawing the same thing in multiple different slices and pictures, so I just hopefully it's clear what I'm drawing. Okay. Okay, so this is the standard way of doing this. We use the RT formula. We can see this transition to a setting where we can reconstruct the interior of the black hole. And now what I claim is that instead of using the RT formula, we can instead use the connected wedge theorem and also figure out when an island forms, but using this other tool, okay, and from this more causal perspective. Okay, so the way to do that, I need to tell you how to apply this theorem. To tell you how to apply the theorem, I need to tell you where to pick the points R1, R2, and C1. Okay, so what we're going to do is we're going to pick R1 and R2 to be at the beginning of the two horizons, right? So I had these lines that define these horizons. R1 and R2 are their starting point. And then C1, you're free to move around, and your choice of where to put C1 is going to define how big of a radiation system you have. Okay, in particular, V is going to be the radiation system. Okay, V was picked out by, in this case, J minus of C1 intersect J plus R1 intersect J plus R2. Okay. Okay. Good. And then what we see is that, okay, so we have these points here, R1, R2. What the theorem tells us is that when that brane anchored scattering region is not empty, then the system V, which here is our radiation, attaches to the brane. And R1 and R2, the earliest time in their future is just the beginning of the black hole interior. And so the causal condition in this theorem, phrased in terms of the black hole language, is just that we're looking for cases where the black hole interior is causally connected to the radiation. Okay, so this is my radiation, and we're just looking for causal curves that travel through the auxiliary geometry out to the radiation system. And then the theorem concludes that in that case, V attaches to the entanglement wedge of V attaches to the brane. And in the island black hole language, what that means is that the radiation system is forming an island. Okay. So the punchline here is just that if the black hole interior is causally connected to the radiation system through this auxiliary geometry, then the radiation forms an island. Okay. There's a slightly awkward thing here in that the radiation system picked out by this point C1 will sit apparently just outside of the Poincare patch. So I've drawn the patch here, and it's these blue, includes these blue regions here. And then R will sit right next to it. And so it looks like it's outside the patch. It's a bit of an illusion though, because this diamond on the boundary, I can think of as being defined by this time slice, but I could also think of being defined by this time slice or the one where I push all the way back to here. So you should really think of this radiation system as living at this sort of scribe plus of the CFT. It's it's at null infinity. Okay. Any questions about this? There's one of the punchlines for the talk. So.
I guess maybe more a comment than a question. I'm not sure what this is going to become, but I guess I would somewhat disagree with the statement you just made in that this black diamond you've drawn can or should be thought of as part of the radiation region. And the reason is that if I want to describe the system, like say as a black hole coupled to a bath, then my usual like Hamiltonian time evolution, like an observer which sees the system as a black hole coupled to a bath, will just evolve me within the blue region. Yeah. And then, of course, you're right. I mean, I have this global picture, and I can say, well, but if I know certain regions on Scribe Plus, then of course, if I'm like it's a global time evolution, I now can predict what's going to happen in my black diamond. But from point of view of like an observer which thinks this thing is a black hole, like it seems like he cannot use he will just not see that the black hole interior is causally connected to anything he has access to. Yeah,
so that I agree with that, but I think the point is that we're not interested in, like when we say, this subregion of or this portion of the radiation reconstructs the black hole interior. We're just making that at the level of like an information theoretic statement. So like it's in principle possible to do some very complicated operation on that system to see like operators in the interior. And so from that perspective, it's okay to use whatever operator or like whatever Hamiltonian I want to evolve back to this radiation system. But you're right that that's not really something that's like natural from the perspective of the like observers in the patch. But yeah, regardless of what Hamiltonian I use, it's still true that like at an information theoretic level, like the information in this black diamond is stored in this like orange.
No, absolutely, I agree with that. Absolutely, yeah.
But yeah, I think this causal relationship between the radiation system and the black hole interior is not apparent from like an observer in here. It's like some it's as you say. I don't think I could put it better, but yeah. Right, yeah.
So are you working in some particular limit where the boundary entropy is much smaller or much bigger than the bulk central charge?
Oh yeah, I guess I skipped that actually. Sorry. So so I said that the tension was large.
But you keep drawing pictures where the tension is 0.
Sorry. Yeah, I do. I keep drawing the t=0 picture here, just because it's very annoying to draw this setup when the brane is like this, because it just obscures part of the diagram.
Except the light cone structure cares deeply about that.
Yeah, the theorem is still true at large tension. So the statement I'm making is still true. Yeah. So basically, the light cones care, right? Because the brane is further away. So like this light ray gets longer.
Right.
And then also this is getting really messy. Also, it will happen that this region here, V, needs to be larger before it starts attaching to the brane. And the theorem tells you that, you know, whenever this light ray can reach the radiation system, that's when this region becomes large enough. And maybe I'll also comment that in the particular solutions I studied here, where we have a constant tension brane and pure AdS, the theorem actually goes in both directions. So this light ray attaches to the radiation system exactly when the entanglement wedge of V connects to the brane, and that's for all tension, all constant tension. I don't know if that answers your question.
I'll have to think about it.
Yeah. Okay.
Thanks.
But yeah, you're right that I'm really interested in this limit, but I'm drawing this picture just because it diagrammatically is annoying. But. Right.
Yeah, and I was just wondering sort of what happens to, for instance, this entanglement wedge. And you say the V needs to be bigger. Does that mean you have to push it up the boundary?
You bring C up later.
So it's sort of later along the boundary.
Yeah.
Yeah. Okay.
But the arrangement of all the parts is still the same. It's just things are V would be larger and this point would be up here, kind of thing.
Okay, but you never run into a contradiction where you sort of need V to be bigger than it can be on the boundary. So you don't leave the Poincaré patch ever, I guess is what I'm asking.
Oh no.
Yeah. Okay.
So I have a question also. I mean, is there a way to, first of all, understand this intuitively? And secondly, is there a way to connect this to something like the page time?
Yeah, so you can see, the page time here would be, so I can put this point C here at different values of the time, right? And I can keep, for small times, this region will be small and it will be attached, the V will not be attached to the brane, right? And then I can move it up and up, and at some point there'll be a transition to this phase. That will be the page time, right? So that's where the entropy starts becoming smaller again, is after these surfaces change configuration. And so
that should be a function of the number of modes that are being radiated and the entropy of the original black hole or something like that. Is that clear from that calculation?
Yeah, so the page time in this picture will be like the light travel time of this null ray, and that will be controlled by the tension. So by how far away the brane is into the bulk, right? So larger tension will push me to later times.
That's right, yeah. But sorry, isn't the page time the location of the green line?
Oh yeah, sorry. Okay, it's this over 2. Yeah.
Yeah. Okay.
Yeah.
But sorry, I mean this T/2 does not have any operation. I mean, you got to convert it to something which a guy
Yeah, you
living in the
have to-
blue things like can live, right?
Yeah.
So it's like something like retarded time or.
Yeah, I mean, okay, yeah, you would look at where these orange things are, and then look at your time coordinate in the patch, and this would correspond to some time. But yeah, and then it's, you know, this light travel time is controlled by the tension, and then that's controlled by the ratio of the edge central charge to the CFT central charge. And you can think of this as you know, the edge central charge, that was like the number of black hole degrees of freedom, and C was the number of radiation degrees of freedom. And so this ratio sort of controls how fast information can escape from the edge into the CFT. So that would be a more microscopic picture of what's happening.
If I can ask another question, have you ever tried to actually, I mean, do this computation? Because it seems like very, like in this kind of models, right? Like what you're proposing here seems like very easy to do. It's like you shoot a light ray in like a AdS geometry, and you know, calculate some time, and then you convert it into like a time.
Yeah.
Whereas, I mean, in the paper that like Ignacio and I wrote with Rob Myers and a couple of others, we have a value for such a scenario for the page time as like depending on the number of dimensions and so on. And
right,
I think that would be kind of
yeah,
very nice to see if you could just get the same value this way. I mean, I guess you would, but
yeah, I mean, you have to get the same value just because this in this case where you have constant tension and pure AdS, the region picked out by doing this procedure of this connected wedge theorem kind of thing is exactly equivalent to what you get by thinking about
right.
surfaces.
I guess my point is it just like seems way easier the way you do it than the way we had to do it.
Yeah, in that it just sort of directly geometrizes the page time, right? Like it's sort of just this time. But yeah, as you say, you have to think about what that means in the patch, and so that would be I guess you'd have to do some coordinate transformation and think about that a bit. But, yeah.
Can I follow up on Tom's question? So
yeah.
In AdS3 here, with the brane being AdS2, if you do a more standard entanglement entropy calculation, one has to give a prescription of what is the theory on the brane, what is the gravitational theory in the brane. And since it's going to be two-dimensional, if you just do the standard Randall-Sundrum procedure, you're going to get some weird two-dimensional theory. And on top of that, I guess the sort of standard thing is to put JT gravity. Of course, you could put maybe something else. So what I don't see in your description is how does this travel time of the light ray and so on know about the action that you're putting on the brane?
Yeah, I haven't thought very hard about that, but it's a good question. I mean, so the light travel time just cares about, I mean, okay, so I guess in this model, the light travel time does care about the action on the brane, because the action on the brane that I put was, you know, K minus L matter, and this was proportional to the tension, right? And so here somehow I picked a very simple action, and there was just this one number, and then that ended up controlling the light travel time. I guess, you know, if you pick some other action, then you have to think about solving these equations I said before, and figuring out where the brane is going to sit in the bulk. So figuring out its embedding equation, and then just from this embedding equation, you're going to get the light travel time. Yeah, so I don't know. I mean, I don't know what the details would look like there, but yeah, but by this procedure of solving like this boundary condition, the light travel time is sensitive to the brane action. And then, yeah, the theorem tells us that so long as that brane action is one where the stress tensor is going to satisfy the null energy condition, then somehow this is all going to work out correctly for you.
Yeah, there's actually, I mean, if I can just like leave one last comment, I don't want to hold you up too long, but I mean, I think it's an interesting question that Ignacio posted here, because what you can do is you can sort of like, you add like a constant tension to your brane, which maybe is your tunable parameter, and then you add an intrinsic gravity action to your brane, and you sort of add a counter term tension. And it turns out you can fine tune these things in such a way that the brane stays at whichever location you choose it to be on, while you're still free to change the intrinsic gravity action to the brane. But what that does is it can delay the onset of this page phase, or like of the
I guess you get terms. You get like a term associated with like the value of the dilaton that adds.
That's right. That's right.
Yeah. So that would. Yeah, I mean that might make the theorem, like turning on those terms might be what actually makes the theorem not go in the other direction. I would have to think about which way that goes, but yeah, I'm not sure. I'd have to think about this in detail, but it'd be interesting to see how this plays out for sure. Okay. Okay. Well, already at an hour. That's okay. This is one of the punchlines. So if the organizers want to cut me off at some point, please do so. I won't be offended. But I'll try and tell you a little bit about how you actually argue for this theorem being true. Okay, so this is this like
time, by the way, if it's
okay,
a reasonable time, go ahead. No problem.
Okay. Yeah, it might be 10 minutes or something like that, but yeah, maybe even 15. Okay, anyway, so there's a particular way of thinking in quantum information theory that's going to get us to this theorem. Okay, and what we're going to use is this idea of what's called a quantum task. Okay, and a quantum task, it's just a quantum computation, but it's one that occurs in the context of spacetime. Okay, as is often the case in quantum information theory, it's convenient to introduce two players here, Alice and Bob. There's going to be Alice, who's going to be the person receiving inputs, doing something to them, and then producing the corresponding outputs. And then there'll be Bob, who's the person who prepares the inputs, gives them to Alice, and then receives the outputs from Alice, and will do something to check that they're what they're supposed to be. Okay. And then what's new here and what's important is that the inputs and outputs occur at specific locations in spacetime. Okay. So here's an example of what that looks like. I have a task. It's happening in 1+1 dimensional Minkowski space. There's a point here called the input point where Bob is going to give to Alice some quantum system A. Okay. And then up here, there's some output point or output location where Alice gives to Bob, or where what Alice's task is, what she's supposed to do is to give A back to Bob. Okay. So this is a very simple example of a task. Okay. Given a task, we can ask various different questions about it. One basic thing we could ask is just with what probability can you complete the task? Okay. So we can try and compute this number, the success probability. And something to point out about this is that this thing depends in an important way on not just what the inputs and outputs are, but also where they occur in spacetime, right? So the way I've drawn it, R is in the future of C. This would be easy to complete. The success probability would be 1. If I put R down here, though, outside the future of C, then the success probability would be basically 0. Okay, so that's one kind of thing we can ask. And it's I'll just point out that this number we can compute is sensitive to the causal features of the task. And then the second thing we can do, we can ask a different kind of question, maybe have a bit more of a refined question, which is if we assume the success probability has some lower bound, in some cases we'll be able to argue that, or prove that Alice has certain resources. Okay. And the resources here might be something like, I don't know, certain classical information, or maybe entanglement distributed in spacetime in a certain way, something like that. Importantly, the resources are not just like what Alice has, but also when and where she has them, right? Because when and where she has them they can be more or less useful for actually doing the task. Okay, now what I want to do is to apply this kind of task and certain results about these tasks in the context of holography. So the way I'm going to do that is to follow the following procedure. So I'm going to define a task in the bulk. Okay, we'll call it T. And then I'm going to identify in a particular way that I'll describe on the next slide some dual task in the boundary, some corresponding task in the boundary. And then I'll assert that what we'll use is that the success probability in the bulk should lower bound the success probability in the boundary. The way to think about this is just to say that if I can think about some process that happens in the bulk that completes the task, then that process is also described in the boundary description, and so also completes the task, and thus I get this inequality. It's an inequality, not an equality, because I want to think about the bulk low energy effective description. And so there will be things that happen in the CFT that are not described in that low energy description. And this sort of one-wayness, right, means that the boundary describes the bulk low energy physics, but the bulk low energy physics doesn't describe all of the boundary. And that is what leads to this being an inequality. Okay. Basically what I'm going to do is by thinking about the bulk, and in particular the bulk geometry, I will make some statements about this side, right? So maybe I'll say that this is some number alpha that will tell me that the success probability in the boundary is lower bounded. I want to think of this as basically a constraint on the CFT and the state that's in the CFT. And then I want to try and turn this into some kind of statement about the CFT that I might actually care about, right? Like this is a really weird kind of a statement about a CFT. I want to make this into some statement about, say, entanglement in the CFT. And in particular, we're going to get some statement about the mutual information. Okay, good. Right, so the task, so to identify a boundary task, what we want to do is start with the bulk picture. So we're going to pick some task where the inputs and outputs are off at infinity. And then the corresponding task in the boundary will just identify those points at infinity with points in the conformal boundary like we normally would. And then we'll say that the inputs to this point here are the same as the inputs to this point here. These, the task specifies what quantum information you get at C1 and what quantum information you have to return to R1. In the bulk and boundary picture, the degrees of freedom that quantum information is put into will look very different, but that's okay. At the quantum information level, it's the same thing. Okay. Yeah, and so this is the kind of reasoning I'm going to use to argue for the theorem. I'll just flash the theorem up just to remind you of it. Here's the task I'm going to use. So the task has one input and two outputs, and the input is this state here, HQB. And B and Q are both bits. They're 0 or 1, okay? H is the Hadamard. It takes 0 to plus and 1 to minus. Okay, so that means that this state, if Q is 0, is either 0 or 1. And if Q is 1, is either plus or minus. Okay, and then your goal, the task you have to complete, is to bring B to both R1 and R2. Okay, good. And from here, the argument is pretty quick. So what we do is we put this task called the monogamy task into AdS. So we have some point down here, C1, R1, and R2. That's the input point for my task, right? So the HQB comes in here. And then following the conditions of the theorem, I'm going to pick a case where this thing is not empty. So the brane anchored scattering region is not empty. And then I'm going to specify that the information about Q is recorded into the brane. Okay. And so when this is not empty, it's very easy to do the task, right? So you just bring HQB to the brane, learn Q, undo HQ. So you just have the state B, and then B comes out, then you can send B out to R1 and R2. So your probability here is 1. Okay. And then we just think about this again from the boundary perspective. So in the boundary, we have the same task. The causal structure looks a little bit different. And what I claim is that if the probability here is 1, then it implies that this information Q was stored in V, where V is this future of C1 and past of R1 and R2. And the intuition there is basically that, okay, in this region, you have HQB. So you in some sense have B, but you don't know which basis it's stored in. And you're going to need to find out the basis information to learn B while you're still inside of B so that you can send it out. Okay. Because if you learn it too late, if you learn B up here, then you can't get it to R1 and R2, or if you learn it over here, then you can't get it to R1 and so on. Okay. So if the probability is 1, then Q is in B. Okay. And that's basically enough to get you the statement, because we just combine the various pieces I've given you together. So we say that, okay, in the bulk, the probability is 1 when this region's not empty. The bulk probability lower bounds the boundary probability. So now this is 1, but then we said that being 1 implies that Q is inside of V, right? Q was in the brane. V is this boundary region. And so for the boundary to know Q, it must be that its entanglement wedge attached to the brane. So yeah, because this is how entanglement wedge reconstruction works. V only knows Q if it's inside the wedge. Okay, and that gives you the theorem, right? So it says, in the bulk, when this region exists, you can do the task. When you can do the task in the boundary, it must have been that Q was inside of V, but Q was on the brane, and so you have this island thing. Okay. So that's everything. I apologize for going over time. Just summarize by saying, okay, so we thought about these quantum tasks. This sort of captures like relativistic aspects of quantum information, thinking about how quantum computations happen in a space-time context. Applying that to AdS CFT, we get this connected wedge theorem. And then in the context of these BCFT models or brane models of black holes, then we got this sort of interesting statement about relating the auxiliary geometry and causal features of that auxiliary geometry to the formation of an island. So thank you.
Okay, Alex, thank you very much. We already had several questions, but I guess we have time for a couple more. So please go ahead.
Yeah, I asked already a few questions, so if somebody else wants to go
ahead.
first. But otherwise, yeah, I was just wondering, sort of like, have you thought about how to turn this around? Like, what would be conditions for arguing that, once you have an entanglement wedge, there is some sort of notion of like scattering point?
Yeah, it's a really interesting question. I think it comes down to this kind of so if I have a I wonder what the best way to describe this is. So it might be best to, right, okay, so we could probably think about it this way. Have this region here, V. And then, yeah, the statement was, when you scatter in the bulk, then this wedge attaches to the boundary. I guess the thing is, so you could imagine a scenario where Q is stored inside of V, but the bulk description, so in principle, okay, there's something you can do to the subregion V to like get Q out. But in the bulk picture, that might correspond to doing some, maybe very, very high energy process. And so the bulk description of like getting Q out might not look geometric at all, right? And so, yeah, so I think for this reason, the theorem doesn't go both ways. And then it's not totally clear to me how one might get around that kind of an obstruction. Like, yeah, maybe it would be like some different notion of an entanglement wedge that would be like the things that you can access. That would be like the portion of the bulk that you can access by doing some restricted set of operations in the boundary, like some that kind of keep you in the low energy subspace.
Right. I guess that would be like if you had the other direction, that could be nice because you could make an argument of like, okay, I have a bunch of conditions which tell me when I can sort of realize something as a local semi-classical thing.
Yeah,
in the bulk.
Yeah, I think that's what it. Yeah, you somehow have to think about like, yeah, the class of things you can do while staying in the code subspace, so to speak.
Right.
Yeah, and yeah, it's not clear to me how to move forward there, but I think conceptually that's where it's at.
Okay, thanks.
Yeah.
Can I ask then, what was so special about, why did you need to choose D equals 2? I mean, I don't see exactly what would differ in like be different in higher dimensions. Like, it seems that you could presumably do a similar thing with, instead of maybe light rays, there would be null surfaces or something like this.
Yeah, I mean, I just actually haven't thought about it that hard. So possibly yes, but yeah, I've thought about the theorem I gave at the beginning. Or I guess I can phrase it in terms of this theorem because it's more familiar. So for the theorem to be non-trivial, what you wanted was that this scattering region was not empty, so that you can actually conclude something. And then what it's going to conclude is that like the entanglement wedge of V is attached to the brane. So it's not empty. But what you could have is you can have settings where, let's draw it this way. V might just be like this region here, right? So V could already be attached to the brane, in which case the entanglement wedge always is going to include the brane. And so if you've chosen your points such that this happens, then you haven't really learned anything from the theorem. And it's easy for me to construct cases in low dimensions where that's not happening, and V is out here. And then the thing to think about is just that, can you get this kind of a situation in higher dimensions? So if I pick these 3 points, can I ensure that V won't just be attached to the brane like by default? Otherwise, the theorem will be kind of trivial. And yeah, I'm not sure actually if that happens or not. I know that like the analogous question for this other theorem, which I've thought about harder, you kind of only fall into trivial cases of this theorem in higher dimensions. Well, it's a bit of a complicated story, but like in global AdS 3+1, the other theorem is trivial, and then in non-global AdS 3+1, you can construct non-trivial cases. And anyway, so I'm actually not sure what the story is for higher dimensions in this picture, and but you know, I think something conceptually similar should be true. It's just I'm not quite sure how to set it up.
Okay, thanks. Last questions. Well, I guess there's no further questions. We thank Alex again for this very interactive